In part 2 of the experiment, we'll be using a circuit that has R2 and this nickel chrome wire in series. In order to place this wire in series with R2, we'll connect each end here, the low end, into this thumb screw. And the other end here, this blue wire, and with these connections we can use our banana cable to create a series circuit. We'll treat the blue as the high end of the wire and the black as the low end. So our current will come in from the function generator on this side of R2, pass through R2, through this wire, through the blue wire to the end of the nickel chrome on the right hand side of the screen, through the nickel chrome wire, and return along the black to the power supply. So this is our return. And this will be our high side. Before we power the circuit on, we do want to take a resistance reading of the wire using our multimeter. And we will note this in our data sheet, 3.678. Notice the units here, this is ohms, not kilo ohms. The wire has very low resistance. This is intentional by design. Wires should not have high resistance. They're designed to carry current without interfering with it. All right, series circuit. R2 into our nickel chrome wire, and then return to the power supply. For this portion of the experiment, we want our V in to be 12 volts. That's the voltage that we read on R2. We're going to measure that with our oscilloscope, channel 1, here, and measure on the high side of R2. We'll power on our function generator, move our scale here on channel 1 to 2 volts per division. We are currently outputting 1, 2, 3, 4 boxes times 2 volts per division, that is 8 volts. We will use our output level to increase that to 12 volts. 6 boxes, 1, 2, 3, 4, 5, 6 times 2, 12 volts. We're interested in how voltage changes if we include more or less of the wire in our circuit. So we can measure the voltage across the entire wire directly as we normally would on channel 2 by placing channel 2 on the high side of the wire, moving to channel 2 and moving to the appropriate scale. Here I am over in the millivolt range on my scale. I'll position this waveform so that the bottom is along one of the horizontal lines and the peak is along the central ruler. 1, 2, 3, 4.3 millivolts times 10. 43 millivolts is the voltage across the wire. But to include more or less of the wire, we'll use this slider. By depressing the plunger, we can interrupt the circuit. We will do that with this red wire. Connecting this to our volt reading. Now, looking at channel 2, if we include more or less of the wire, we see a larger voltage drop for more wire included in the circuit, and a smaller voltage drop for less wire included in the circuit. The measurements we'll make now are voltage versus length. Starting at 10 centimeters, we'll place our plunger at the 10 centimeter mark, and we will measure the amount of voltage. Here, the waveform is very small. I will increase the scale to 5 millivolts per box to increase our precision. This is 1.2 boxes. 1.2 at 5 millivolts is a 6 millivolts, 0.6 millivolts. 6 millivolts. And then as we move up every 10 centimeters, we will take another voltage reading. At 80, 1, 2, 3, 4, 5, 6.7 boxes at 5 millivolts. 33.5 millivolts voltage drop for 80 centimeters included in the circuit. Once all of these measurements have been taken, we'll do some calculations to calculate the resistance for each length included in the circuit, and then plot length versus resistance of the wire. The slope of that will allow us to calculate the resistivity of the material, this nickel chrome of the wire that we're using.